Polarizing light microscopy uses a method of contrast enhancement which improves the quality of image of birefringent materials as compared to other techniques like dark field and bright field illumination, etc. You may be wondering what birefringent materials are. Birefringent materials is a material whereby the reflective index is dependent on the polarization and the propagation of direction of the light. It is also used to observe and photograph specimens that can be seen mainly because of their optically anisotropic character. Specimens that has optically anisotropic character is quite similar to birefringent materials, where its behavior is dependent on the direction of propagation of the light. Polarized light microscopes have a high sensitivity. As such, it can be utilized for both quantitative and qualitative studies for a broad spectrum of anisotropic specimens. Based on how the electric field is aligned, the polarized light can be categorized into three types of polarization: linear polarization, circular polarization, and ecliptical polarization. I am just briefly mentioning them. You do not need to go into details for these. The picture on the top here shows the overview of the different components in the polarizing light microscope. And the picture on the bottom here shows the direction of light traveling in a polarizing light microscope from the light source all the way to the eye. So, how does polarizing light microscope works? When a beam of white unpolarized light passes through the first polarizer, the beam of light is split into two components which are polarized in mutually perpendicular directions. These two components are called ordinary ray and extraordinary ray. When setting up the polarizing light microscope, the polarizer and the analyzer should be 90 degrees apart to create extinction, such that the field of view becomes as dark as possible.
The first major component in a polarizing light microscope is the polarizer. There are two polarizers. The second polarizer is usually referred to as an analyzer. The polarizers contain a prism which is created by specifically cutting and bonding together a crystals of doubly reflecting material, like calcite. The polarizer is positioned in the light path somewhere before the specimen, where the analyzer is placed in the optical path length between the objective rear aperture and the observation tubes. Over here shows how the polarizer and the analyzer looks like. On the diagram over here, you can see that the polarizer is positioned below the stage at the base of the microscope. The analyzer, on the other hand, is placed between the objective and the ocular lenses. The next component is the condenser. The condenser should be strain-free and achromat. Achromat is a lens that transmits light without separating it into constituent colors. The condenser should also have a numerical aperture range between 0.9 and 1.35. Another component is the rotating circular stage. The stage can be rotated 360 degrees. The stage uses a precision ball bearing to have good control over the verniers, which allows user to read the angle of rotation with an accuracy of near to 0.1 degree. There is also a clamp which is used to steady the stage so that the specimen can be arranged at a fixed angle with respect to the polarizer and analyzer. Like every other microscope, polarizing light microscope also have objective. The range of magnification of the objective ranges from about 2 times to 100 times. The most common objective used are 4 times, 10 times, 20 times, and 40 times. Compared to ordinary microscopes, the average numerical aperture of the 20 times and 40 times polarized light objective is usually 10 to 25% higher, as observation of cornerscopic interference patterns calls for high numerical aperture. The objective must be stress and strain-free. Any stress in these optical components will result in a significant degree of anisotropic character called internal birefringence. This will affect the specimen and its observation, and can frequently cause the interpretation of images to be extremely difficult. If there are stresses or strain in the optical system, The background would appear to be blue, gray, or brownish when observing the specimen. A system with no stress or strain will appear as just black. Another major component in a polarizing light microscope is the retardation and accessory plates. There are two types of accessory plates, the retardation plates and compensators. The retardation plates have a fixed optical path length, while the compensator have varying optical path lengths. The compensator and retardation plate have varied anisotropic plate thickness and optical characteristics. The reason is to create a specific optical path length difference. The three most common retardation plates have optical path length differences of an entire wavelength ranging between 530 and 570 nanometers, one half wavelength ranging between 260 and 280 nanometers, and a quarter wavelength ranging between 137 and 150 nanometers. A full retardation plate creates the interference color having a tint similar to the first order red magenta color. The microscope is furnished with a slot to store a compensator or retardation plate. Compensators and retardation plates are also widely used for qualitative application such as control of background illumination or to enhance the contrast and visibility in weak birefringent specimens. The last major component is the eyepiece, but since it was previously mentioned in stereo microscope and compound microscope, I won't mention about it again.